Hi everyone, thanks for bearing with me through these 3 videos for Thursday's lecture. So this is the 3rd video explaining a series of concepts in NLP that are going to be important to be familiar with in order for the transformer and transformer-based language models, which is what we'll talk about next week, to make sense. All right, so this video is going to introduce sequence-to-sequence models. Sequence-to-sequence models take a sequence as an input and produce a sequence as an output. And they exist in all sorts of problems: audio, vision, language, and multimodal. And so you're going to see sequence-to-sequence models crop up across the course, and what can be their advantages and disadvantages and what sorts of tasks they may be most suited to. This lecture is going to introduce sequence-to-sequence in the context of neural translation. I know that not a lot of people in this class necessarily care a lot about neural translation per se, but this is helpful. First of all, because it's going to provide a bridge to introducing transformer language models, because the original transformer paper was a sequence-to-sequence neural translation model, and also because it will allow us to introduce attention, which to the best of my knowledge was first developed in the context of neural translation, and attention is going to be the key ingredient of transformer models, both in language and vision. Okay, so by way of introduction, we'll introduce what machine translation looked like in the pre-deep learning era, which serves as another important contrast for understanding the power of neural methods compared to previous approaches, which this is going to be, again, driving home the theme that the model can learn better representations from being exposed to lots of data than through human engineered rules, which I think in some ways is like a feature of human learning as well. Like my 3-year-old daughter knows how to talk really well, but it takes a lot of effort to teach her, okay, car starts with the C sound and dog starts with the D sound. And people people learn how to use human language very well without necessarily understanding all the rules of how it works. And they learn through being exposed to empirical examples. Same thing with deep learning. All right, so to briefly talk about statistical machine translation, which is what predominated in the pre-deep learning era. So the first thing I want to say is that these systems were extremely complicated. Many engineers worked over many years to create a system that gave sort of reasonable results. If anybody in the class was kind of old enough to use Google Translate a really long time ago, you'll kind of appreciate what I mean by sort of reasonable results. Okay, so the basic idea is to use data to estimate a probabilistic model. We want to find the best sentence in language Y given a sentence in language X, and we can use Bayes' rule to break this into 2 components that are learned separately. So probability of X given Y models how words and phrases should be translated from X to Y given parallel data. And the probability of Y models how to write a good sentence in target language Y, and it's learned only from data on language Y. So to learn a translation model in this fashion, we need parallel data. That is pairs of sentences translated from Mandarin to English by people. So to learn translation, we can rewrite this P of X given Y as P of X comma A given Y, where A is the alignment, which is a word level correspondence. So just to give some examples of alignment and why it's sort of complicated, you can have spurious words in one language but not another. You can have one-to-many alignment. You can have many-to-one alignments. You can have many-to-many alignments. And annotating data on alignment is very, very, very costly. You need people that speak both languages well and that can annotate these potentially complicated patterns. And so statistical machine translation learns P of X and A given Y as a combination of many factors. So the frequency with which particular words align, conditional on position in the sentence, the fertility of words, which is on average how many words in the target language correspond to a given word in the input language, and a variety of other statistics computed from parallel data. And so you have these very complicated human engineered models built up over many years. And you're going to need parallel data on alignment, which is costly, and a bunch of human engineered statistics, which is a hard problem. Neural machine translation is going to help us on both of these fronts, as we'll see. So we have some intuition for how to compute P of X given Y from alignment, and P of Y is a language model, which we've already seen. And so how are we going to compute the argmax here? One idea would be to calculate every possible Y, i.e. every possible sentence in English, and compute the probability. So like obviously that's not computationally feasible. And so instead use a heuristic search algorithm to search for the best translation, discarding possibilities that are too improbable. So the process of finding the best translation is called decoding. And you can think of this as considering different hypotheses in a tree, but you prune the tree as you go along. All right. So the state-of-the-art statistical translation models were extremely complex, as I've said before. Hundreds of important details are beyond what I just talked about. Systems had many subcomponents, tons of features engineering. You had a very large number of people work on designing these systems over many years, and it was a very, very specialized endeavor. Okay, so now neural machine translation. This is showing kind of a benchmark, and neural machine translation is just going to come and circa 2016 start, totally blowing it out of the water. And so the benchmark data set often used in this domain is called BLUE, Bilingual Evaluation Understudy. And it compares machine translation to several human translations and computes similarity by comparing n-grams and penalizing translations that are too short. Okay, and so you had these statistical translation systems engineered by hundreds or thousands of people over many, many years, and they get beat by a neural machine translation model engineered by a few people in a few months, which I think is just pretty mind-blowing. But again, it's the same theme that we've seen elsewhere in the course. Deep learning can make models both more accurate and way more efficient, way more accessible to develop. So deep learning has actually made these domains that used to be incredibly specialized, and you just had to have an enormous amount of knowledge to really work in them, because you had these rules, and then you had exceptions to the rules and exceptions to the exceptions, and it became this very complicated system, and turns it into something like very straightforward. It would take me an entire course, if I knew anything about it, to teach statistical machine translation after this lecture. And if you had enough of a background kind of in deep learning, you could implement a neural machine translation model with much, much more modest effort. All right, so let's talk now about how neural machine translation works. Neural machine translation is a sequence-to-sequence problem. And here you see a decoder RNN, which, watch the videos for Thursday in the order that they appeared on the Canvas. So if you are watching this and you haven't watched the first video about language modeling, go do that and see what an RNN is. All right, but we have an encoder RNN that is taking a variable length sequence as an input, and a decoder RNN that is taking that is outputting a variable length sequence as an output. And remember, what an RNN does is allow us to have variable length inputs and outputs versus like a COMNET, which we saw Tuesday, where you have a fixed size output. All right, and so a sequence-to-sequence model is taking a sequence as an input and producing a sequence as an output. So it's essentially like a many-to-many model. Okay, and so the decoder portion of this, which you see as the green, is a language model. It's predicting the next word. It's going to be conditional because its predictions are conditioned on the output from the encoder, which is fed in the source sentence. And so you see the way that this model works is that you put in the first word that you want to translate, and you get your hidden state, and you encode that, and then you multiply it by your weight matrix, and you pass in your next input, and you add and squish, and you do that so on and so forth. And in reality, this could be an LSTM, it could be a transformer, you could be using kind of different models on either side of this. But you have this, I guess in this case, this cannot be a transformer the way this is drawn. Suppose that this is an LSTM. And so we have our input sentence and we have these hidden states. And then when we get the last hidden state of the input, we're going to pass that, the last hidden state of the encoder, that's going to be passed to our decoder. And our decoder is going to start decoding the sentence conditional on that last hidden state from the encoder. Okay. And so how do we train a sequence-to-sequence model? And so sequence-to-sequence is going to be trained end-to-end. And so we're going to be jointly training our decoder and our encoder. We'll need two sets of word embeddings. So we need to be able to feed, say, the French words in this example into the RNN and output the English words. And unlike, when we want to run this model at test time, we don't feed the output back in, we feed in the target sentence in training it. Okay. So before I go into how to decode, I just want to go back to the original picture and make sure everybody understands sort of the basic intuition. So we have an input sentence and we're feeding that input sentence in sequentially. And at each time step, we're combining the input, the representation of that input word with the hidden state. For example, adding them using weight matrices and then using a nonlinearity. As I said, kind of underneath this, I think traditionally you would have used something like an LSTM. And then we take that last hidden state or that last representation from the encoder, and we use that to condition the decoder, which then at each time step predicts an output word, which is just kind of the most likely word given that representation, and then also passes on a hidden state, which is used kind of along with the previously predicted word to predict the next word in the sentence. So this decoder is a language model that's going to generate the target sentence conditional on encoding. So how do we do decoding? So greedy decoding would just take the argmax at each step of the decoder. Just take the most probable word. But the problem with this is this leaves you no way to undo your decisions. At the other extreme, you can consider all possible translations. At each step T, you'd have to keep track of V to the T possible translations, where V is the size of your vocabulary. You're obviously not going to do that because that is completely infeasible. And so beam search, which you'll often see used in practice at each step, keeps track of the K most plausible partial translations, where K is the beam size. And the plausibility score is just the probability of the sequence. And you'll see beam search used a lot in NLP. When a hypothesis produces the N token, you put it aside and you continue exploring other hypotheses, and you stop either once you reach time step T, which is a hyperparameter that you would choose, or once you collected at least n completed hypotheses, which is again a hyperparameter that you would need to choose. Longer hypotheses will have worse scores. You could fix this by normalizing scores by length when selecting the final hypotheses. All right. So there have been many improvements to the initial sequence-to-sequence model for neural translation that we just saw, but one is particularly fundamental and a major motivation for why we're talking about neural translation and talking about it at this particular point in the course. And so what is the problem with the model that I just showed you? Remember, the way that the encoder works is you're taking the input word and you have this hidden state. And then you take the last hidden state from your encoder, and the decoder is conditioned on only that last hidden state. And so you are forcing all information about the sentence to be encoded in the final vector from the encoder, because that is the only thing that gets passed to the decoder. And so it's essentially creating this information bottleneck between the encoder and the decoder. And so you cannot just take all your hidden states and concatenate them together and pass them to the decoder, because you have a variably sized input. You don't know how long that sequence is. And remember, at its core, neural networks is just a bunch of matrix algebra operations. And so you cannot have variably sized things that you're multiplying by. It's not going to work, right? And so you cannot just concatenate those hidden states from your encoder, because the entire point of an RNN is that you can have a variably length input sequence. But you need like a fixed size input to pass to the decoder. All right. And so attention is going to be what lets us get that. So at each part of the decoder, we're going to use a direct connection to the encoder to focus on a specific part of the source sentence. And this effectively allows us to pass information from a variably sized encoder model to the decoder in a learnable way. And this concept has really transformed NLP. It's going to seem like a very simple concept when you see it, but it's actually really, really important. And so I'm going to introduce kind of attention and kind of the way that it was initially used in neural translation. And so we have now we've passed the input through our encoder, okay? And we want to start decoding it. And so we have our start token there with the decoder, and we're going to take, suppose for the sake of illustration, although attention doesn't have to be computed this way, that we're going to compute attention by taking the dot product between that first state of the decoder and each of the encoder states. And we're going to use that to get an attention score. Okay, so we're taking a dot product between the vectors, and we do that with each of the hidden states of the encoder, and that's going to give us an attention score for each of the encoder states. And then we're going to compute an attention distribution, which we can do just by taking the softmax to turn the scores into a probability distribution. And you can see in this particular time step, we're mostly focusing on the first encoder hidden state, which would make sense in the context of neural translation, right? Because oftentimes the first word in the translation is going to come from the beginning of the sentence. All right. And that gives us an attention output, which could essentially be like a weighted sum of the encoder hidden states. And so this attention output is going to mostly contain information from the hidden states that receive high attention, which in this case is the first hidden state. And then we can just concatenate that attention output, which is going to be a fixed size with the decoder hidden state, and use that to compute the first word of the output sentence as before. And then we're going to do that again. This time we're going to take the dot product between the second hidden state of the decoder and each of the encoder hidden states, get an attention score, get the distribution from that by taking a softmax, use that to create the weighted sum of the encoder hidden states, which is our attention output, concatenate that, and so on and so forth until we reach an end token. Okay. And the really cool thing is that when you train this model and you see what the attention distribution looks like, it looks like alignment. But this model was not trained with data on alignment. It just had the sentence in English and the sentence in French, and the model learned the alignment. And remember that alignment data, like what you needed for statistical machine translation, was super, super costly to collect because a human had to sit there and code the alignment. And that's just a super tedious task. And instead, just by having these translations, the model learned through attention what alignment looked like. And we didn't need to have these really costly labels, which is just this enormously powerful thing. There's other advantages to attention. It solves the bottleneck problem that we just saw. It also helps with vanishing gradients by providing a connection to faraway states. So again, this is going to be a recurring theme kind of in this class when we see major advances in the literature, that oftentimes they occur by helping us to solve vanishing gradient problems, because that allows us to have larger and larger networks that give more and more expressive possibility. So attention is going to have implications far beyond machine translation, and we're going to talk, the transformer paper, which we'll spend all of Tuesday talking about, is called Attention is All You Need. So we'll spend a lot more time talking about attention. But just to give sort of a basic definition, given a set of vector values and a vector query, attention computes a weighted sum of the values that is dependent on the query. So the query tells us where to focus in creating the weighted sum of values. So in short, attention creates a fixed size representation of an arbitrarily sized set of representations given other representations, which is the query. So suppose that H1 to Hn, which are encoder states, are the values, and S is the query. In the example we saw, that was our first decoder hidden state. Attention always requires computing an attention output, A, from the attention scores. And there's several different ways to compute these attention scores. E, you could have dot product attention if the dimensions of S and H are the same. That was what I showed in the example. You could have multiplicative attention. You could have additive attention. As I said on Tuesday, we'll see in detail how attention works in the transformer, but this is the basic idea and where this concept of attention came from. And so this is, I think, the final ingredient that we need for introducing the transformer to make sense. And I will see everyone on Thursday, and also get the lecture on the transformer uploaded soon. Thank you.